An abundance of energy, solar power's potential. Our sun, a blazing sphere of hydrogen and helium, bathes the Earth in a constant stream of energy. Imagine the power of 173,000 terawatts. That's the amount of solar energy that reaches our planet every single moment. To put that in perspective, it's over 10,000 times the total energy consumed by all of humanity. This staggering figure highlights the immense potential of solar power, a source of clean and sustainable energy that dwarfs our current energy needs. The sun's energy is not only abundant but also readily available. Unlike fossil fuels buried deep underground, sunlight reaches us directly. We don't need to drill, mine, or transport it. All we need to do is capture it. This simple fact makes solar energy a compelling solution to our growing energy demands and the urgent need to transition away from polluting fossil fuels. As we look to the future, a future where our energy needs are met without jeopardizing the health of our planet, harnessing the power of the sun becomes not just an option, but a necessity. The sheer abundance of solar energy, coupled with its accessibility, makes it a cornerstone of a sustainable future. The science of sunlight to electricity, how solar panels work. The magic of solar energy lies in its ability to transform sunlight into electricity, and at the heart of this transformation lie solar panels. These panels are composed of smaller units called solar cells, typically made from silicon, a material found abundantly in sand. But how do these seemingly simple cells orchestrate such a remarkable transformation? The secret lies in the structure of silicon and the clever engineering of solar cells. Each silicon atom is connected to its neighbors by bonds, and these bonds hold electrons in place. Solar cells are designed with two distinct layers of silicon, the N-type layer, which has extra electrons, and the P-type layer, which has spaces for electrons called holes. When these two layers are joined, a fascinating interaction occurs. At the junction between the N-type and P-type layers, electrons from the N-type layer are drawn to the holes in the P-type layer. This movement of electrons creates an electric field, a region where an electric force can be felt. Now when photons from sunlight strike the solar cell, they knock electrons loose from the silicon atoms. These freed electrons, driven by the electric field at the P-N junction, flow in one direction, while the holes they leave behind flow in the opposite direction, generating an electrical current. The power of the sun in your hands, output and scalability of solar panels. The process of converting sunlight to electricity begins at the smallest unit, the solar cell. A single silicon cell, despite its remarkable ability to harness the sun's energy, produces a relatively small voltage, typically around 0.5 volts. However, just like individual batteries can be combined to power larger devices, solar cells are connected in series to form modules, significantly increasing the overall voltage. A typical solar panel module comprising multiple interconnected cells can produce around 12 volts, a voltage commonly used in residential settings. The scalability of solar panels is one of their most significant advantages. These modules, each capable of generating usable electricity, can be assembled and connected together in countless configurations to meet a wide range of energy demands. Whether it's powering a single home, a sprawling industrial complex, or even an entire city, solar panels offer a versatile and scalable solution. The ability to easily scale solar panel systems makes them suitable for diverse applications. From small off-grid systems powering remote cabins to massive solar farms generating electricity for entire communities, the possibilities are virtually limitless. This inherent scalability, combined with the decreasing cost of solar technology, is rapidly transforming the energy landscape. Overcoming the challenges, a bright future for solar energy. Solar energy, despite its immense promise, faces a number of challenges that must be addressed for it to reach its full potential. One of the primary concerns is the uneven distribution of sunlight across the globe. Regions near the equator receive far more sunlight than those closer to the poles. This disparity necessitates innovative solutions, such as long-distance energy transmission or a distributed energy grid, to ensure equitable access to solar power. Another challenge is the intermittent nature of solar energy. Sunlight is obviously unavailable at night, and its intensity can fluctuate throughout the day due to cloud cover or weather patterns. To overcome this limitation, efficient energy storage solutions are crucial. Batteries, pumped hydro storage, and other emerging technologies play a vital role in storing excess solar energy generated during peak hours for use during periods of low sunlight or high demand. Despite these challenges, the future of solar energy remains bright. Advancements in solar technology are constantly improving the efficiency of solar panels, allowing them to capture more sunlight and generate more electricity. Furthermore, the cost of solar panels has plummeted in recent years, making solar energy increasingly competitive with traditional fossil fuels. In many parts of the world, solar energy is already the cheapest and safest form of electricity generation, particularly in developing nations where access to reliable electricity is limited. The transition to a future powered by the sun is well underway. As research and development continue to push the boundaries of solar technology, we can expect even more innovative solutions to emerge. From floating solar farms on reservoirs and lakes, to solar roof tiles that seamlessly integrate with existing architecture, the possibilities for harnessing the sun's energy are boundless.